Lecture 1, Neodymium, Magnets of Empire. Start with a constraint you can feel in your hands, torque density. Think about wanting a small, lightweight electric motor to shove a heavy car up a hill without screaming like a blender. You also want that motor to sip electrons instead of guzzling them, to stay efficient even when it's hot, and to deliver that instant low-speed pull we've all come to expect. The usual answer is a permanent, magnet-synchronous machine with a heart made of neodymium iron-boron magnets. Those magnets are where the physics gets glamorous and the supply chain gets messy. They are why a motor the size of a watermelon can launch 2 metric tons of vehicle into traffic with no drama. They are also why the most strategic grams in a car are not the lithium in the battery, but the neodymium, and its friends, embedded in the rotor, shielded by coatings, locked into a carefully engineered microstructure, and budgeted down to the last percentage point by engineers who have nightmares about demagnetization curves. According to the United States Department of Energy's supply chain assessment in 2022, China has historically accounted for roughly 90% of the world's sintered neodymium iron-boron magnet manufacturing and about 90% of rare earth metal refining, the stages where the motor's oomph truly gets made. That concentration is not a plot device, it is the playing field. So, what exactly is neodymium? In plain language, it's a silvery, reactive metal in the lanthanide family. Its atoms bring something special: unpaired electrons tucked deep inside, insulated from the outside world by other electron shells. Those sheltered unpaired electrons give neodymium a knack for strong, directionally stable magnetism when it's part of a crystal with iron and boron in just the right proportions and microstructure. You don't need chemical symbols to get the gist. Neodymium's inner electrons behave like a stubborn chorus line. Align them well and they'll hold their pose against heat and stray fields. Add a touch of dysprosium or terbium at the grain boundaries of that crystal, and the chorus holds even when the stage gets hot. This magnet family keeps winning in the real world because of that property, unmatched magnetic energy density. In practice, that translates to smaller motors and higher efficiency for the same job. Geologically, neodymium isn't rare so much as rarely found in a place you'd enjoy mining. It shows up chiefly in 3 geological situations. First, in bastnasite mineral deposits associated with carbonatite complexes. The classic examples are Mountain Pass in California and Bayan Obo in Inner Mongolia, where a fluorocarbonate ore carries a suite of light rare earth elements, including neodymium. Second, in monazite, a phosphate mineral that likes to hang around in heavy mineral sands on ancient shorelines and riverbeds from India to Australia to the southeastern United States. Monazite is rich in lanthanides, neodymium included, but also typically contains thorium, which makes permitting and managing the residues a serious business. Third, in the iron adsorption clays of southern China, and similar clays now being prospected from Madagascar to Myanmar, where tropical weathering liberated rare earth ions and left them loosely clinging to clay surfaces, so loosely that they can be washed off with a simple salt solution. According to the United States Geological Survey's reports in early 2025, these are the major resource classes that feed the world's rare earth supply. China still dominates overall mine output, and even more so the downstream separation steps that turn a mixed rare earth soup into individual high-purity oxides and metals. Let's walk the process, quickly but properly, because the bottlenecks hide in the verbs. Start with ore. If it's bastnasite, you mine it and crush it, then put it through flotation, where bubbles and surfactants carry the rare earth minerals to a froth and leave the waste rock behind. Now you have a concentrate, still messy. You roast it to drive off the pesky carbonates and fluorides in a controlled way, then leach it with acid. If your ore is monazite, you have to be more careful, roast it to crack the tough phosphate lattice, leach it, and have a parallel plan for those thorium-bearing residues that will outlive everyone in the marketing department. If it's iron adsorption clay, the chemistry on paper is gentler but in practice more treacherous. You percolate ammonium salt solutions through the clay to exchange the rare earth ions off the clay and into a pregnant liquor. A research paper in 2020 revealed why this works so easily. In those clays, the rare earth ions are truly just adsorbed on the surface as hydrated complexes, loosely held on kaolinite clay, so a modest ionic nudge sends them into solution. The catch is what you leave behind in that soil if you're sloppy with your ammonium and let heavy metals wash downstream. No matter the ore, after leaching you face the infamous separation problem, 17 elements with maddeningly similar chemistry, all swimming together. The industrial answer is solvent extraction, carried out in long rows of mixer-settler units. Imagine hundreds of stages, each one a tiny nudge that gradually teases the elements apart. You keep running those liquid extractions until neodymium, praseodymium, dysprosium, terbium, and their friends are finally each traveling in their own lane. You precipitate the target elements out as oxalates, then calcine those to oxides, and at last you have the powders that mining company investor decks love to brag about. Then comes metallurgy, turn that neodymium praseodymium oxide into metal, or straight into alloy, either by a metallothermic reduction, basically using an even more reactive metal to yank the oxygen away, or by molten salt electrolysis if you need higher purity. Cast the resulting alloy quickly into thin strips to freeze a fine microstructure, use hydrogen to make those strips crack and crumble neatly along their grain boundaries, jet mill the pieces into powders only a few micrometers wide, press that powder in a strong aligning magnetic field, then sinter, heat treat, and apply a protective coating. And if you want your magnet to perform at high temperature without loading it up with heavy rare earth elements, there's one more trick: grain boundary diffusion. That means wicking a small amount of dysprosium or terbium into the magnet along the grain edges. This puts a tough little shell of high coercivity material around the grains so the magnet's inner strength is protected. When things get hot, without penalizing the room temperature performance too much. The United States Department of Energy's Magnet Supply Chain Report in 2022 lays out this whole choreography, along with an uncomfortable truth. The hardest know-how to replicate in the entire chain lives right here, in those two stages: solvent extraction chemistry at scale, and magnet microstructure control at scale. Here's where the supply chain stops being a map and turns into a funnel. The world still leans heavily on China for most of that separation capacity, metal making, and magnet manufacturing. Those are the choke points that decide whether your shiny new electric vehicle factory hits its quarterly production target or sits waiting on a pallet of magnets. The International Energy Agency's outlook in 2024 put it plainly: as clean energy demand rises, the share of key production steps concentrated in a few countries has actually increased, with China leading the refining and magnet stages that matter for neodymium. That concentration isn't just geographic, it's institutional and technological, and it's been reinforced by policy. Beijing removed its old export quotas on rare earths in 2015 after losing a case at the World Trade Organization, but since then it has tightened its grip in other ways, consolidating domestic producers into a few large groups, enforcing strict quotas on how much rare earth or an oxide can be produced each year, and, critically, imposing controls on the export of magnet manufacturing technology. In mid-2024, China rolled out new regulations that created a traceability system for rare earth products, essentially putting the government's hand on every step from mine to magnet. The point isn't secrecy, it's leverage. If you control the stages that decide whether a magnet meets spec, you control more than a commodity, you control timelines. For an automaker or a turbine maker, that means you either build alternative supply chains or accept that policy risk is now part of your bill of materials. If you prefer names and addresses, the picture is starting to evolve, but it still speaks the same basic language. In January 2025, for example, MP Materials announced that its new facility in Fort Worth, Texas, began producing neodymium praseodymium metal and even trial batches of sintered magnets for automobiles. They expect to ramp toward on the order of 1,000 metric tons of finished magnets per year, supplying General Motors with magnets made from ore mined and refined in the United States. That's a milestone: metal and magnets made domestically, with a supply line tracing back to Mountain Pass, California, but it's one facility against a globe of demand. According to MP's own updates, Mountain Pass produced tens of thousands of metric tons of rare earth oxides in 2024, including about 1,300 metric tons of neodymium praseodymium oxide. Translate that, the upstream mining and oxide production is scaling up, but the downstream magnet-making lines are still the limiting theatre. Australia's Lynas Corporation has been the non-Chinese counterweight for over a decade, feeding a separation plant in Malaysia with concentrate from its Mount Weld mine. They recently added a cracking and leaching plant in Kalgoorlie, Western Australia, which began producing mixed rare earth carbonate in mid-2024. It wasn't smooth sailing. Something as mundane as a sulfuric acid supply disruption forced Lynas to shut down and then restart the new plant. And in Malaysia the company faces a constant regulatory drumbeat over how to handle the low-level radioactive waste from Mount Weld's slight monazite content. Malaysia's government extended Lynas's operating license in late 2023 but with conditions and a firm timeline to develop a solution by 2026. If you want a picture of how environmental constraints play into supply security, that is it right there. You can have the ore and the funding, but if you don't have a credible plan for the residues, the train doesn't leave the station. Meanwhile, Allied efforts are also taking shape on a modest scale. In the United States and Europe, several new magnet manufacturing projects backed by government support and industry partnerships aim to come online by the mid-2020s. For instance, a German-based magnet producer is constructing a sintered neodymium iron-boron magnet plant in the American South with help from defense funding and an offtake agreement from a major automaker, targeting production by late 2025. An American startup, having acquired equipment from a former Hitachi magnet factory, produced its first batch of neodymium iron-boron magnets at a pilot facility in early 2025 and plans to scale up to a few thousand tons per year in the coming years. In Europe, a Canadian-led company is building one of the region's first magnet plants in decades, in Estonia, to supply European electric vehicle and wind turbine makers with magnets by around 2025 or 2026. Additionally, a long-established rare earth alloy producer in the UK is expanding into a new facility in France to provide magnet metals and alloys for European manufacturers. Even Japan, which still produces a few thousand tons of neodymium magnets each year and remains the largest source outside China, has focused on incremental improvements and overseas partnerships rather than large new factories at home. All of these efforts, from Texas to Tallinn to Tokyo, share a goal: to cultivate some magnet capacity outside China's shadow. By 2025, however, they remain tentative first steps. They will collectively add up to only a small percentage of global output initially. China's unmatched scale, lower costs, and deep know-how mean it will continue to dominate magnet production through this decade, but at least alternative supply trickles are beginning to form. Zoom out to the world level, tonnage and prices, and you can feel the market's pulse. The United States Geological Survey's summary for 2025 reported that world mine production of rare earth oxides hit the high hundreds of thousands of metric tons in 2024, nearly 400,000, in fact. China still produced the lion's share of that ore, with the United States, Australia, Myanmar, and others contributing smaller portions. But here's the key for neodymium: it's not about the raw tonnage in the ground, it's about separated oxide, then refined metal, then finished magnets. The price behavior echoes that reality. The average price of neodymium oxide surged in 2022 amid strong demand and worries about supply, then slumped through 2023 and into 2024. As of mid-2025, the price sits well below the panic levels seen in 2011 when Chinese export quotas briefly sent rare earth prices into orbit. If you were around when neodymium metal shot past $300 per kilogram in mid-2011, you remember how quickly "we'll just redesign it" became the bravest sentence in automotive engineering. The lesson that survived that crash is simple: Price spikes tend to be frequent and violent when a single policy lever controls both the flow of material and the know-how to process it. Don't romanticize the word rare. The ore bodies themselves impose plenty of work and worry. Bastnasite from places like Bayan Obo and Mountain Pass comes with a lot of fluorine and carbonate that you must neutralize or drive off during processing. Monazite brings that phosphate matrix and its habit of smuggling along thorium, which means you need a plan to safely store or dilute those radioactive leftovers for literally centuries. The iron adsorption clays look gentler. After all, you're mostly using salt water to wash metals off clay, but reality is less idyllic. Those operations often involve hundreds of hoses laid across a hillside, turning rainstorms into unplanned chemistry experiments if you're not careful. Recent studies continue to show the trade-offs when using ammonium sulfate to leach those clays. You might get good rare earth recovery, but if you cut corners, you can upset the soil chemistry or pollute groundwater with alarming speed. In audio terms, the quiet parts of the process, the parts that don't make it into the glossy brochures, where the soundtrack gets expensive. So why does neodymium keep winning in all these applications, even with that baggage? Because of performance that matters in the real world. In an electric motor, neodymium iron-boron magnets let you shrink the rotor diameter, reduce the amount of copper windings, and hold efficiency across a wide range of speeds and loads. In a wind turbine, using a direct drive generator built around permanent magnets means you can eliminate the gearbox entirely, trading a whole box of gears and moving parts for a carefully engineered ring of magnets that doesn't need oil changes and doesn't risk mechanical failure of gear teeth. The US Department of Energy's models, and plenty of industry experience, capture the scale of this effect. A direct drive offshore wind turbine can contain hundreds of kilograms of magnet material per megawatt of capacity. That is exactly why wind farm designers fought for direct drive designs. The reliability and maintenance calculus favors magnets when you're dealing with salt spray, high altitudes, and multi-decade lifespans. In electric vehicles, multiple automakers and suppliers often cite a figure on the order of 1 to 2 kilograms of neodymium iron-boron magnets per vehicle for the traction motors, give or take depending on the model and performance requirements. That number has exceptions on both ends and it evolves with design trends, but it gives you an idea. These magnets are not token materials, they are critical to why an EV drives the way it does. They're the reason procurement managers look at magnet supply contracts the way pilots look at fuel gauges. Of course, there are ways around using so much neodymium, and engineers explore them whenever the trade-offs make sense. Induction motors that have no permanent magnets can do the job. Tesla famously used an induction motor in its first high-performance Model S sedans, with excellent high-power performance and no reliance on rare earths. Flood an induction machine with coolant and let it spin fast, and it will laugh off heat all day. But if you compare it to a magnet-based machine, you'll usually pay a penalty in size or inefficiency at partial load. You need a bit more bulk, or you lose a bit of range. Ferrite magnet motors are another alternative. They use cheap and abundant ceramic magnets, basically iron oxide mixed with barium or strontium, which means you can sail through a rare earth shortage without breaking a sweat. But ferrite magnets are comparatively weak, they are plucky rather than mighty. Engineers can partially compensate by clever design, changing the geometry of the motor, tweaking the pole counts, using smart control strategies, and sometimes that is enough for a given application. Samarium cobalt magnets are yet another niche solution. They are the quiet professionals of the magnet world, with magnetic properties that hold up at higher temperatures and a natural resistance to corrosion. The catch is that samarium cobalt magnets contain cobalt, which carries its own geopolitical baggage and price volatility, and samarium itself isn't exactly falling from the sky either. These alternatives all find uses. You might see ferrite or induction motors in entry-level EV models where cost is king, and samarium cobalt in a jet engine or an oil drilling tool where temperatures are extreme. But on the whole, none of these beat neodymium magnets for the combination of strength and compactness in most vehicle and renewable energy scenarios. Then there are attempts to stretch neodymium itself further. One famous example came from Toyota in 2018, when researchers there announced a new magnet that used substantially less neodymium by substituting some of it with lanthanum and cerium. Now, lanthanum and cerium are light rare earths that are usually abundant byproducts in rare earth production, often considered cheap ballast in the ore stream. Toyota's trick was to accept that magnet performance would suffer if you simply removed some neodymium, and then to counteract those losses through clever materials engineering. They shrank the grain sizes in the magnet to boost its strength, and they used grain boundary diffusion of a small amount of heavy rare earth to maintain coercivity, resistance to demagnetization, despite having less neodymium overall. The public headline for this was, "Magnet uses less neodymium." The quieter headline was, "We stopped reflexively dumping dysprosium into the whole magnet and instead placed heavy elements only where needed." By refining the grains and surgically reinforcing the boundaries, they made a magnet that could work in slightly less demanding parts of a car, think electric power steering motors, which get hot but are relatively small and cost-sensitive, without betting the entire drivetrain on a brand new material. The elegance of that pivot wasn't in the press release. It was in understanding where physics is merciful. If you try to yank neodymium out of a traction motor magnet and demand the exact same performance and temperature tolerance, you're signing up for years of pain and probably disappointment. But if you target a friendlier application where the magnet's job, while important, isn't absolutely existential, physics will shrug and say, "Sure, that could work." Piloting a new magnet material in a power steering unit instead of the main traction drive is good, responsible engineering. It nudges the overall supply risk down without pretending a miracle material is going to save the day. It also creates a subtle shift in the market dynamics. Suddenly you're buying a bit more lanthanum and cerium on purpose, which takes some pressure off the neodymium bottleneck and finds a use for elements that were previously almost a waste product. According to Japan's public research programs in the late 2010s, a significant fraction of rare earth innovation has been exactly this kind of industry housekeeping, using what we have more cleverly and then enjoying the side benefit that it looks like geopolitical savvy. All these moves share a theme. Substitution in this arena is a gradient, not a binary switch. You decide what performance you can afford to lose, or what complexity you're willing to add, in exchange for reducing dependency on a risky element. Product managers might love to announce that they've eliminated rare earth magnets, or cut dysprosium content in half, but the motor designers in the back room are working with dials, not on-off switches. They might reduce the magnet size and lean more on the steel design for a bit of extra reluctance torque. They might tweak a cooling system to make a magnet run a few degrees cooler, so they can use a slightly less exotic alloy. They might quietly qualify two different motor designs for a vehicle, one using the primo magnet and one using a cheaper substitute, so that if material prices go wild, they have a plan B ready. In practice, many automakers have done exactly this, offering a high-end model or trim that uses a neodymium magnet motor for maximum performance, and a lower-end trim or variant that uses either an induction motor or a ferrite-assisted motor to save cost and avoid supply risk. Even wind turbine manufacturers sometimes keep both direct drive, magnet, and geared, no magnet, designs in their product catalog, so they can pivot if they absolutely must. The key is that these choices are very situation-specific. A delivery van that drives predictable routes at moderate speeds might tolerate a less efficient, magnet-free motor to save money, whereas a luxury performance car that promises snappy acceleration on a hot August day will happily pay for neodymium magnets to keep that promise. Now, how do the choke points in the supply chain actually bite? Start with separation, the step where you pull the rare earth elements apart. On paper the chemistry looks almost mundane. Mix phases, let ions partition between them, repeat. But making thousands of tons per year of neodymium oxide at 5 nines, purity, 99.999% pure, give or take, while simultaneously producing praseodymium, dysprosium, and terbium to spec on adjacent lines is a control problem and a capital problem. It's not a textbook operation, it's an operation that lives or dies by on the job. Expertise and consistency. Then there's metal making, turning those oxides into metal of the purity and consistency that downstream alloy casting expects every time. Then the alloy and magnet fabrication, strip casting that must freeze the alloy into a narrow grain size distribution, hydrogen decrepitation that should crack the material at the right places, pressing and sintering steps that must lock in the easy magnetization direction precisely where you want it, grain boundary diffusion that adds dysprosium or terbium exactly where each grain needs a little extra courage. The Department of Energy's 2022 assessment was blunt about this. The world is running thin on capacity that can meet the highest automotive and aerospace specs. And that blunt reality is why export controls on the know-how, on the people and technology, not just the raw materials, matter so much. Policy moves amplify the physics. We've already mentioned how China removed its old export quotas years ago but then pivoted to other methods of control. For example, in April 2025, China abruptly started requiring special export licenses for certain high-performance rare earth magnets. Shipments that would have gone out on Monday were suddenly stuck waiting for paperwork on Tuesday. Exports of magnets from China plummeted that month. Some reports say they were cut in half, because companies were grappling with an opaque new application process that sometimes demanded hundreds of pages of documents. For a few weeks, the global supply chain was on edge. According to industry reports and even public statements by automakers, at least one US car plant had to halt production temporarily because the specific magnets it needed got caught in that bureaucratic slowdown. It took high-level negotiations and a bit of face-saving on both sides for the logjam to start clearing by early summer 2025. That little crisis underscored a point: you can have trucks still hauling ore and factories technically ready to work, but if the legal definition of a compliant shipment changes overnight, everything grinds to a halt. A magnet maker who could buy alloy ingots from a third party on Monday might, by Wednesday, be required to prove those ingots came from an approved source and have a paper trail back to a licensed mine. Compliance officers love that kind of traceability on paper. In practice, it turns a month of production into an audit exercise. Prices twitch because lead times suddenly twitch, and lead times twitch because everyone who must prove custody of each atom is suddenly chasing paperwork instead of making product. By the same token, when enforcement of regulations tightens, say, Beijing cracks down on illegal or off-quota production in a grey area of the market, supply volumes dip and the premium for fully sanctioned material rises. When enforcement relaxes or an economic slowdown makes everyone a little less scrupulous, extra tonnage quietly finds its way to market at tempting prices. In that environment, a magnet maker's procurement team isn't just buying oxide or metal, they are buying risk and insurance. They have to decide how much extra inventory to buy, or how much they trust a given supplier's paperwork, or whether to pay a bit more for a magnet made entirely outside the choke point country. These are quiet calculations that happen in supply chain war rooms, and they ultimately show up as either a price premium or a production hiccup down the line. Redesign thresholds bring a bit of order to all this chaos. Auto companies, for example, won't lightly throw out a well-developed motor architecture. There's usually a break-even price point, or price band, for magnet material above which they seriously consider switching a platform to a different motor type for the next redesign cycle. That threshold isn't a single magic number. It's more like a wide fuzzy zone, because it depends on your product's positioning, how much customers care about efficiency, what the charging or fueling infrastructure looks like, and how your vehicle dissipates heat. If your car or truck absolutely needs every drop of efficiency and that delightful low-end torque, then magnets are hard to beat and you'll endure a lot of price pain before you jump ship. If your product is more about keeping costs down and you can live with a few percentage points less efficiency, because you have a bigger battery or you assume a different usage pattern, then you'll lean the other way. In small devices like headphones, drones, or tiny actuators, the threshold is astronomically high, meaning you'll tolerate insanely high magnet prices, because energy density and compact size are paramount, neodymium wins until its price truly goes through the roof. In wind turbines, the threshold is trickier. It's not about one magnet's cost but about the lifetime cost of the turbine. A direct drive turbine might justify a high magnet price because it saves you maintenance on gearboxes and higher reliability at sea. You could run the numbers as a net present value, fewer boat trips for repairs and more uptime generating electricity. The decision is rational, but it can sound emotional in the boardroom because entire factory investments and maintenance strategies hinge on a few price inputs. Recycling sneaks into that conversation like a cheerful realist. Take factory scrap, the bits of magnet material left over when you slice, dice, and grind magnets into their final shapes. That's the low-hanging fruit of recycling. You know the composition, you know there's no surprise radioactive element in it, and you have a lot of it in one place. That scrap can often go right back into the alloy, making process with only modest processing. The real glamour, though, is in recycling end-of-life products, trying to fish magnets out of things that were never designed to give them up. Think about it, a hard disk drive or a loudspeaker or an old electric motor doesn't advertise, "Hey, I've got some neodymium in here." The magnet is often glued in, coated, and tucked away in a form that's really inconvenient to extract. The enemies of magnet recycling are coatings, adhesives, and silence meaning the device isn't telling you there's a magnet inside. Adhesives are designed so that human hands never need to separate that magnet again. Coatings are designed to withstand pretty much anything a recycler might throw at a product. The clever technique that researchers and startups have honed to break this cycle is hydrogen decrepitation applied to scrap devices. Basically, you use hydrogen gas to embrittle and crack the magnets in situ, without shredding the entire device. The magnet breaks apart, often losing its adherence to the metal it's attached to, and you can pry out or shake out the magnet pieces without pulverizing everything else into mixed waste. Those pieces can then be cleaned up and resintered into new magnets, ideally without ever returning all the way to a dissolved, separated state. As elegant as that sounds, scaling it up is messy. To recycle effectively, you need collection networks. Someone has to actually gather all those dead hard drives or motors. You need a clear assignment of who pays for pulling products apart. And you must carefully control things like oxygen contamination in the scrap. If you just toss a bunch of old magnets in a scrap bin and melt them down, you'll get a metal ingot, sure, but it might be full of oxygen or other impurities. And any magnet made from it will be a B student in a class that only graduates valedictorians. According to a cadre of national laboratories and university projects over the last decade, the physics of magnet recycling is surprisingly cooperative, meaning you don't lose a ton of performance if you do it right, but the economics aren't so kind. Today, recycling magnets only really works when you either have legislation that forces the issue, for instance, requiring companies to take back old equipment or include recycled content, or product designs that make disassembly and recovery easier. Without one of those, it's tough to get enough clean magnet material back cheaply enough to make a dent in primary demand. We're likely to see recycling help more and more, especially for large, magnet-dense items like wind turbines being decommissioned or the guts of data centers being upgraded. But in 2025, it's still a supplement at the margins, not a river you can float the whole industry on. Environmental and social costs are not footnotes in this story. They're gatekeepers. The bastnasite route to rare earths brings a lot of carbonate and fluorine to the party. The chemistry to neutralize those is old and well understood. You can precipitate out fluorides, bubble off carbon dioxide, etc., but you have to run it with discipline, no leaks, no shortcuts in storing the resulting muck. Monazite, as we noted, carries thorium and other unwelcome guests. Extracting rare earths from monazite safely means committing to secure, monitored storage for that thorium for decades, maybe centuries. That kind of planning usually outlives management teams and political administrations, which is a big challenge in itself. The iron adsorption clay operations initially sold themselves as the easy, lunch bucket mining job of the rare earth world, you weren't building a huge chemical plant, just washing dirt with mild salts. But then reality kicks in. If you don't manage the runoff and the erosion properly, you get landslides laced with ammonium and heavy metals, and suddenly the gentle route looks pretty damaging. None of this is an argument against producing rare earths, it's an argument for going in with eyes open that the quiet verbs, words like collect, neutralize, store, monitor, remediate, are the adult responsibilities in mining. Regulators and communities have made it abundantly clear that their patience does not extend to mysterious ponds of wastewater or ambiguous answers about groundwater safety. That's why the projects that last, in China or elsewhere, tend to be the ones who handle waste like it's part of the product. They budget for it, engineer for it, and sometimes talk about residue management like a utility talks about keeping the lights on. If you want a human-scale sense for where control really sits in this supply chain, try following a mine-to-motor journey in your head. Picture a haul truck dumping fresh ore into a crusher at dawn. At a bastnasite deposit like Mountain Pass, the crushed ore goes through flotation. Little bubbles carry the rare earth-bearing minerals to the surface in a froth while the barren rock sinks away. The concentrate that leaves the flotation plant is still a mongrel mixture, useful in the way flour is useful before it becomes bread. Next, you roast that concentrate, which changes the chemical personality of the minerals. It drives off those pesky carbonates and fluorides that would resist your acids later, and it primes the ore's crystal lattice to crack more easily. Then you persuade the minerals to give up their riches, you leach with acid, under carefully controlled conditions, measured in degrees Celsius and pH, not in vague terms like pretty hot, or kinda strong. The result is a pregnant liquor, a cocktail of all the rare earth ions dissolved together. It's as much a bureaucratic challenge as a chemical one, because now you have a liquid that contains a family reunion of lanthanides that really don't want to be separated from each other. You've got to give each relative a code, a ticket, and put them on separate trains. Solvent extraction is the long hallway where that promise is kept, one tiny step at a time. In those mixer settlers, an organic phase and an aqueous phase dance past each other, and specially formulated extractant molecules shuttle rare earth ions back and forth, separating them by the slimmest of preferences. Someone watching over that process might look bored, but they're actually shepherding a flock of error bars, making sure each stage does just enough and not too much. Little by little, you pull praseodymium apart from neodymium, dysprosium apart from terbium, until you have streams pure enough to name without apology. You precipitate those purified streams as oxalates, fire them into oxides, and now the powder in your hand is no longer just rare earths, said with an eye roll. It's neodymium praseodymium oxide, or dysprosium oxide, with a specification sheet you can attach to a purchase order. According to the U.S. Geological Survey in 2025, the capacity to do this separation at scale remains the most concentrated step in the entire chain. In other words, those long rooms full of mixer settlers are as much geopolitical assets as they are factory equipment. That oxide, however, is not yet a magnet. It's just feedstock. So the journey continues, ideally somewhere closer to the motor factory, because it's easier to schedule trucks on a highway than ships across an ocean. Let's say we're still following that Mountain Pass material, which means we're headed to a metal and alloy plant in Texas. There, the oxide powder becomes metal. One way to do that is metallothermic reduction. Introduce a reactive metal like calcium that has a higher affinity for oxygen than neodymium does. The calcium grabs the oxygen atoms and leaves behind neodymium and praseodymium, metal. Another route is electrolysis, essentially zapping molten salts containing neodymium to coax the metal out. Electrolysis can yield very high purity, but it's finicky and energy intensive. Metallothermic is the workhorse for volume. Either way, the prize at this stage is a controlled composition of neodymium, iron, and boron, plus a dash of other elements depending on the grade, that will end up carrying the magnet's personality in its microscopic grain structure. Next comes casting that alloy into a form that we can turn into a magnet. The preferred method for high-performance magnets is strip casting. You melt the alloy and then fling it onto a cold rotating drum or wheel, which splatters it into thin ribbons. Those ribbons cool so fast that the metal's grains don't have time to grow into large, lazy crystals. Instead you get a myriad of tiny grains with the right mix of phases. Now, you take those thin alloy strips and introduce them to hydrogen gas. Neodymium has this helpful quirk: it readily absorbs hydrogen, and in doing so, it expands and makes the alloy crumble along the grain boundaries. This step is called hydrogen decrepitation. It's like a well-timed joke that cracks the material along just the right lines. After the hydrogen does its work, you remove it, often by heating in vacuum to drive it back out, and you're left with a powder of magnet alloy. That powder needs to be refined further, literally refined, in terms of particle size, and aligned to turn it into a magnet. So we jet mill it, which is basically using high-speed particle collisions to grind the powder down to very fine particles, on the order of a few micrometers across. We also take great care that these particles don't pick up oxygen or other impurities during this stage, because freshly milled rare earth alloy powder will oxidize in a heartbeat if you let it. Now comes grain alignment and pressing. The powder is placed in a die and subjected to a strong magnetic field, so strong that if you wore a wristwatch into the room it might pull the hands off the dial. That field coerces each tiny particle's internal magnetization to point in the desired direction. While holding that field, we press the powder into a solid shape, often a block or a ring. Then we sinter it, heat it up to a temperature where the particles start to fuse together, but not so high that the alloy's phase structure melts or shifts. During sintering, those particles knit themselves into a nearly fully dense solid, all while hopefully preserving the alignment we imposed. If the application for this magnet is going to be hot, cyclic, or otherwise harsh, and an automotive motor definitely checks all three boxes, this is when we do the grain boundary diffusion trick I mentioned earlier. We place a small amount of a dysprosium, or terbium-rich compound on the surface of the magnet and heat it just enough that these heavy atoms diffuse a short distance into the magnet along the grain edges. They form a thin shell around each grain that dramatically improves the magnet's high-temperature coercivity, its resistance to losing magnetization when things heat up or when it faces opposing magnetic fields. The beauty is that the bulk of the magnet inside those grains is still the original neodymium-rich formula, which means at room temperature it's as strong as ever. You've just armored it for high-temperature battle. After diffusion, we do a final heat treatment or tempering to stabilize everything. Finally, we give the magnet a protective coating, because neodymium iron-boron magnets will rust away their strength if you give oxygen and moisture half a chance. Common coatings are nickel plating, usually a nickel-copper-nickel sandwich for durability, or an epoxy polymer layer, or sometimes conversion coatings, depending on the use case. With coating done, we then machine the sintered blocks into the precise shapes needed, often arc segments that will form a ring inside a motor's rotor. This machining has to be done carefully to avoid chipping or overheating the magnet, and the shop vacuum has to pull up the grinding dust because that dust is both valuable and a fire hazard. Those arc-shaped magnets we end up with don't look like much to the untrained eye, little dull pieces of metal, each with a thin coating measured in micrometers, each magnetized in a certain direction. A rotor assembly is basically an argument about alignment that you have to win repeatedly. You glue, or otherwise secure, each magnet into its slot on the rotor. You often slip a carbon fiber or steel sleeve around the whole circumference to hold the magnets in when the rotor spins at high speed, because trust me, you don't want magnets flying off at tens of thousands of RPM, and then you balance the whole assembly so that it spins smoothly. And then come the tests that outsiders might consider paranoid, but which the people who design these things consider simply prudent. Thermal cycling. Bake it and freeze it repeatedly to see if any magnet or adhesive loses its nerve. Salt fog testing. Essentially spray a saline mist at the rotor for days or weeks to simulate years of exposure and make sure no little coating defect blossoms into full-blown corrosion. Vibration testing. shake and spin that rotor until it has essentially sung its entire range of resonant frequencies and nothing has come loose or cracked. Only after all that do you test the motor as a whole. If the magnet maker left even a pinhole in a coating, the salt fog test will usually find it. If the sintering step was a tad too hot and some grains lost their alignment, the motor's back electromotive force, or its torque curve will sing off key and alert the engineers that something's off. If the grain boundary diffusion underdid or overdid the heavy rare earth, you'll see it in the motor's performance. Too little dysprosium and the motor starts to fade at the high temperature end of its spec. Too much and it doesn't hit the torque target at room temperature. In the magnet business, a hair's difference in composition or process can matter, and automakers buy the difference between those hairs because their warranties and safety margins are built around motors that behave exactly as expected for years on end. The big news in early 2025 wasn't just that someone in the US made a neodymium magnet that has been done before, but that those magnets passed all these gauntlet tests to be accepted for use in actual cars. It's one thing to make a magnet, it's another thing to make them boringly reliable, over and over again. Traceability has become non-negotiable in this chain. It used to be a nice to have, but now every tote of oxide comes with a document history, which mine produced it under which quota, whether it sat in a warehouse for 6 months or went straight through, whether its calcium impurity content was at the upper allowable limit or safely below. A pallet of finished magnets comes with its own genealogy. New export control rules that took effect at the end of 2023 have made this paperwork a matter of survival for businesses. When a country says, we will restrict the export of certain magnet manufacturing technology, it's effectively saying, we'll sell you the fish, but we won't teach you how to fish. It's not a scandal, it's a strategy. And the counter-strategy is pretty straightforward too. Either slowly and expensively teach yourself to do it anyway, or partner up with someone who already knows how and has a reason to help you build redundancy. The mind-to-motor case study we just walked through is basically that strategy written in steel and epoxy. Let's take a different perspective through the same landscape, a corporate pivot that was disguised as a scientific advance. Back in 2011, the world got a wake-up call that if you tie a critical material like neodymium to a single country's policy, your price chart can suddenly look like a roller coaster. Engineers didn't respond with outrage, they responded with clever engineering. We already talked about Toyota's magnet that used lanthanum and cerium to ease the neodymium burden. That's a case where a company hedged its material risk by investing in materials science and found a partial solution. We also saw what happens when the hedges don't work out. The last rare earth price spike in the early 2010s didn't just inject money into the industry, it also built a museum of overconfidence. Between 2010 and 2015, one famous American rare earth mine went from a celebrated restart to an ambitious reinvention under a plan with a mythic-sounding name. They attempted, in one go, to build an end-to-end rare earth supply chain, mining, concentrating, separating, reducing to metal, making alloys, and turning out high-purity products, all at full commercial scale and all at once. Each individual step was challenging but feasible. Doing them all simultaneously and perfectly. That turned out to be a little too much entropy for one timeline. For a brief period, the market made it look doable, rare earth oxide prices were sky high, investors were optimistic, and spreadsheets were throwing off rosy projections. But by 2015, two things happened. The World Trade Organization case forced China to drop the export quotas, and rare earth prices fell back to earth. Suddenly that project's margin for error evaporated. The new processing circuits the company had installed were finicky. Some days they ran brilliantly, other days they ran into one problem after another. Solvent extraction at that scale is not very forgiving. You can't just invent a new chemical plant and expect it to hum along without months, or years, of debugging. With revenues falling and the process still not fully tamed, the company went bankrupt in 2015 under a pile of debt. Public filings from that period basically show that the debt collectors don't wait for your materials science breakthroughs. The lesson isn't that ambition is bad, the lesson is that in this corner of the periodic table, if your business plan needs the price spike to last until you've ironed out every process kink, you are not planning, you're praying. Price spikes come in months, capital projects and learning curves play out over years. So what went wrong there beyond the price went down? A lot of it boils down to integration risk and timing. They tried to do every value-added step at full capacity without having incrementally earned confidence in each step. If the acid plant had an issue, the whole chain ground to a halt. If the filtration step for precipitating the rare earths didn't like the particle size coming from upstream, suddenly you've got a bottleneck and maybe a silo full of partially processed material with nowhere to go. If the separation train chased maximum purity at the cost of throughput, you might end up with very pure oxides but only a trickle of them, and a warehouse full of unsold, off-spec intermediate that you can't monetize. When prices are high and friendly, you're supposed to use that cushion to debug these issues quietly. When prices are falling and unforgiving, you either solve them fast, or the lawyers show up to sort out the pieces. The revival of that same mine under new ownership after 2017 took a very different approach. They ramped up step by step. They were content to produce a mixed rare earth concentrate or an intermediate product and send it to others for final separation in the beginning, just to get the revenue flowing and to focus on making each step boringly reliable. According to company communications from 2020 through 2024, that patience, proving each verb in the process before stringing them all together, is exactly why the same ore deposit that once broke a balance sheet is now feeding magnets into actual cars. Now, let's follow one more chain, this time in the context of renewable energy, where the maintenance conditions read like a piece of Gothic literature. Consider an offshore direct drive wind turbine, which is basically a giant, slowly spinning generator with a ring of neodymium magnets in place of a gearbox. It's a monument to boring excellence. It has no gearbox to maintain or fail, just a yaw mechanism to turn the turbine into the wind, pitch controls to adjust the blade angle, and that big ring of magnets in the generator. The case for using permanent magnets in these turbines isn't about waving some high-tech banner, it's about arithmetic and cold, hard reliability. If dropping a multi-ton gearbox from the nacelle, the box on top of the turbine, means you avoid, say, 3 maintenance trips per year per turbine, and each turbine produces several megawatt-hours whenever it's running, then over 20 years the numbers add up staggeringly in favor of the magnets. Each maintenance trip you skip is money saved and more electricity generated. The case against magnets is straightforward too. Magnets cost money, and out at sea they live in a harsh environment of salt spray and moisture. The supply chain feeding this design choice doesn't end at the wind farm, it ends at a coating line in a magnet factory, where the difference between an adequate magnet coating and an exceptional one is literally where the microscopic pinholes develop after a couple thousand hours of salt fog testing. According to technical notes from major wind turbine manufacturers over the past decade, the permanent magnet approach consistently wins on uptime and often on lifetime cost. Which is why even when rare earth prices zigzag, we don't see all the wind turbines switching back to gearboxes. Where the real control lies in that scenario is unspectacular. It's in the plating chemistry of the magnet coatings, in whether the adhesive holding magnets in the rotor can survive 20 years of flexing, and in whether the magnet suppliers believe they'll still be getting paid 10 years into the turbine's life. That last one is more about contract and credit risk than about chemistry. Recycling pops up here again not as a savior but as good housekeeping. When a wind turbine is decommissioned or repowered, meaning the old turbine is replaced with a new one, often at the same site, the magnets that come back are large, heavy, and relatively easy to identify and handle. This isn't like scraping tiny magnets out of earbuds. You're dealing with big pieces that you can actually grab. The process to recycle those is basically what we described. Hydrogen cracking to break the magnets apart, carefully stripping off the coatings without letting oxygen flood in, and then reforming new magnet segments from the recovered powder that match the original specifications. Factory scrap is even easier because it hasn't been weathered or glued into some weird assembly. It's just offcuts and reject pieces from magnet production, and it usually goes straight back into the furnace to make new magnets once it's collected. There have been pilot lines in places like Europe and Japan that prove you can do this, magnet-to-magnet, recycling without even going back to separated oxides, preserving a lot of the original microstructure's goodness. The limiting factor is not physics, it's collection and logistics. Wind turbines get decommissioned on schedules, and data center hard drives are retired in batches, which are good opportunities to grab magnets. But millions of consumer gadgets and appliances, they die like houseplants, one here, one there, unpredictably and without telling anyone. For magnets to be recycled out of those, you either need a system that makes it easy for the last owner to send them in, or laws that require companies to arrange take-back and recycling. Both approaches can work. Europe, for instance, leans more on legislation, whereas some companies are designing products to be more recyclable. What won't work is just hoping that scrap magnets will magically find their way out of landfills and into recycling facilities without a concerted effort. Let's shift from the technical chain to corporate strategy. Different companies tackle these risks differently. Some automakers have responded to the magnet supply issue by signing long-term offtake agreements with magnet suppliers or even investing directly in rare earth mining and processing projects upstream. They want a seat at the table of supply. In some cases, automakers have actually taken small equity stakes in mines or processing companies. In others, they've simply locked in multi-year contracts to ensure they get their share of whatever magnets are available. Other automakers hedge their bets by actually designing some flexibility into their products. For example, they might design two versions of a drive unit for an EV, one that uses a magnet motor for higher-end models and one that uses an induction motor for budget models. If magnet prices spike or supplies get tight, they have the option to tilt production toward the induction version. Wind turbine manufacturers similarly might keep a geared design in their back pocket for markets where rare earth sourcing is especially problematic, even while they push direct drive designs for offshore farms where maintenance is a nightmare. Manufacturers of things like washing machines or air conditioners, the kind of products that use small magnet motors, might quietly re-engineer those motors to use 20% less magnet material or to tolerate a slightly weaker magnet, if they see price turbulence ahead. According to industry disclosures over the past several years, the most durable risk response is often the least flashy, it's dual sourcing and qualification. If you can find 2 or 3 independent suppliers who can each meet your specs and you give each of them enough business to keep their production lines warm, you have a cushion. When the crunch comes, you're not the customer with no chair when the music stops, you're the one both suppliers recognize as a steady partner. Buying the absolute cheapest magnet on the market on a quiet day is a thrill, but being the customer who kept up orders during the slow times is what gets you priority delivery during the frantic times. The fiasco file exists to keep everyone humble. The last time rare earth prices went crazy, a lot of earnest plans were drawn up under the assumption that those sky-high prices would hold long enough to justify just about any project. A number of new processing projects looked shiny on paper but turned out allergic to scale up. Some downstream customers boldly announced they would redesign their products to eliminate neodymium entirely and found out, a couple of years later, that clever software and extra copper windings can't always defeat the laws of physics. And we already recounted how one company that owned the world's most iconic rare earth mine blew through upwards of $1 billion chasing an integrated dream, only to go bankrupt when the market whiplashed. The lesson isn't that optimism is foolish, it's that time and risk are Siamese twins in this space. Calendar risk is process risk. If prices are treating you kindly for a while, that's the time to do the unglamorous work, build in some redundancy, get your coating process so consistent that you could run it in your sleep, and turn your pilot plant triumphs into full-scale routine operations before the next squeeze comes. So, what developments could actually shake neodymium's place in the world in the next, say, 5 to 10 years? We can point to a few. One is motor topology. Engineers are finding ways to hide or protect magnets inside motors so that you can use less heavy rare earth and still get good performance. For example, some motor designs bury magnets deep in the rotor. These are called interior permanent magnet machines, in such a way that the rotor's iron actually helps shield the magnets from demagnetizing fields when the motor is spinning crazily fast. That means you don't need as much dysprosium to harden the magnets against those fields. Similarly, clever control strategies can deliberately relieve some burden from the magnets. A modern electric motor might blend a bit of reluctance torque, which comes from the shape of the rotor and doesn't require magnets at all, with the magnet torque, especially at high speeds where the magnets are more vulnerable. It's like having a hybrid between a magnet motor and a reluctance motor, and it can keep the magnets out of their danger zone under certain conditions. Thermal management has also improved. If you can keep the magnet a little cooler with better cooling systems or by smartly managing when you really push the motor to its limits, you can trim down the heavy rare earth content because the magnet isn't asked to perform heroics at as high a temperature. None of this is the stuff of flashy headlines, it's incremental housekeeping, but enough increments add up. Use 5% less dysprosium here, another 5% less there, and pretty soon you've materially reduced the supply risk and cost, without waiting for some new miracle magnet material. Supply chains, too, are adjusting in a quiet way. We're seeing steps to shift parts of the magnet production process, especially separation of the oxides and the manufacturing of the magnets themselves, closer to where the end products are made. In practice, that means projects to build magnet factories in North America, Europe, and Japan, even if they start at a modest scale. It's not that shipping rare earths is hard. You can put a year's supply for a big factory in a couple of shipping containers. It's that having the know-how and capacity distributed gives end users more confidence. If you're an automaker, you'd rather not rely 100% on a single country for such a critical component. So having even one or two qualified magnet production lines in, say, the US or the EU that you can source from might make a big difference to your risk profile. Similarly, there's a push to develop recycling programs that are realistic. Instead of claiming we'll get every rare earth back from every old phone and toaster, companies are focusing on the streams they can actually predict and control, the scrap from magnet factories, the piles of old hard drives at data centers, the magnets from large electrical equipment when it's decommissioned. There's real progress in those areas, automated systems to extract hard drive magnets and process them, for instance. And on the policy side, instead of broad proclamations like, we will achieve rare earth independence, we're seeing more targeted, if boring, measures, funding for facilities that produce oxides or metals, grants to build things like a domestic separation plant or a magnet recycling demonstration, requirements that defense suppliers use magnets from certain places, environmental permits streamlining for processing plants, and workforce training programs to cultivate the specialized technicians who actually know how to do all this. According to strategic plans from several governments in the past few years, the competitive edge in the rare earth game is likely to come from those quiet, behind-the-scenes improvements, the operators and engineers and chemists who know how to keep a separation plant running on spec, or how to achieve a 98% yield on a magnet production line instead of 95%. It's not just about having a rare earth deposit or throwing money at a factory, it's about people and processes. Now, let's bring it down to the consumer level for a moment, because this all might sound very abstract. If you buy a car with a magnet-type electric motor, what you're really buying is a certain driving feel and efficiency. You're buying that strong pull when you hit the accelerator at a stoplight and maybe a few extra miles of range on a hot day because the motor stays efficient even when the battery is low and the AC is cranking. If you buy a car with an induction motor, no magnets, you might not even notice a difference unless you drove the two back to back. But essentially you're betting that the carmaker spent the money they saved on magnets on something else beneficial, like better battery cooling or a slightly bigger battery, and that your driving pattern won't expose the motor's slight efficiency disadvantage at low loads. In the wind energy world, if a utility buys a direct drive turbine, with magnets, it's buying the promise of higher uptime and fewer expensive maintenance calls at sea. A drone hobbyist who buys the latest lightweight motor with neodymium magnets is buying a few extra minutes of flight time that come from shaving every gram. The point is, nobody outside the industry cares about neodymium for its own sake. They care about what engineers and product designers can achieve with neodymium magnets, and what the supply chain can consistently deliver. You can think of neodymium as an entry ticket to certain levels of performance and compactness. When everyone wants that performance, the ticket gets more expensive. When someone finds a decent workaround or demand cools, the ticket price eases. What doesn't change is that some experiences, like a whisper-quiet EV that still pushes you back in your seat, or a wind turbine that goes 5 years without a maintenance visit, are basically only possible with that ticket in hand. Sometimes you'll hear engineers muse about a kind of supermagnet that could replace neodymium magnets entirely, something with high strength, great resistance to demagnetization, no significant drop in performance at high temperatures, no corrosion issues, and, of course, none of the geopolitical or environmental baggage. That idea is almost a form of stress relief, a pleasant daydream, because in reality every material comes with trade-offs. Iron nitride magnets, which some startups are working on, might one day take some roles, but they have yet to demonstrate equal performance in large applications. Ferrite magnets are abundant and cheap but weaker. Every miracle magnet you can imagine tends to violate some fundamental constraint, usually relating to how electron spins work in a solid or how you can process the material. So the more pragmatic path has been to make our current champion, neodymium magnets, less scary to rely on. That means pushing processes to be more efficient and consistent, so supply is stable and costs come down, and pushing designs to be more forgiving, so we don't need the magnet to be a superhero in every situation. There is certainly glamour in discovering a brand new magnetic material. Researchers still publish new candidate materials now and then, but there's often more immediate benefit in making an old material more reliably excellent at mass scale. You can actually hear that philosophy if you talk to people who manufacture magnets. They don't romanticize the alloy itself, they romanticize the days when nothing goes wrong on the production line. The sound of a stable process is silence, no alarms ringing, no pile of rejects growing in the corner, no phone calls from an unhappy customer saying, "Hey, the batch you sent us isn't performing to spec." From the mine all the way to the motor, the neodymium story that really matters isn't the occasional headline about a new deposit or a sudden price spike. It's the craft of keeping thousands of little steps within control so that when a motor is built and switched on, it behaves utterly unremarkably, exactly as expected, day after day. That doesn't make for a movie trailer voiceover, but it's what determines who wins in this supply chain. Put on a hard hat and follow 1 stubborn gram of neodymium from rock to rotor, and you appreciate every link. Dawn in the Mojave Desert is pink and quiet until the haul trucks at Mountain Pass mine rumble to life. Bastnasite ore isn't glamorous, it's beige, dusty, and mostly composed of minerals that aren't of interest. You blast the rock, load it up, and crush it. In the flotation mill, a cloud of bubbles and collectors tease the rare earth-bearing minerals to the surface, carrying neodymium along, while quartz and barite and other gangue minerals sink back down to be tailings. The concentrate that comes out of flotation is improved, but still far from pure, useful in the way flour is useful before it becomes bread. So you roast the concentrate, driving off the carbon dioxide and neutralizing the fluorides that would otherwise devour your equipment or resist leaching. Now the rare earths in the ore are in a more amenable mood for strong acids. You leach the roast with acid, dissolving the rare earths into that pregnant solution we talked about. That solution is a who's who of the rare earth family, all the light rare earths like cerium, lanthanum, praseodymium, neodymium, plus a bit of samarium, europium, gadolinium and maybe some heavies if the ore had any, all jumbled together. At this stage, it's as much a triumph of logistics as chemistry to handle it. Next comes the solvent extraction hall, where with a combination of kerosene-based solvents, extractant molecules, and a precisely orchestrated waltz of mixing and settling. You separate that family of elements one tiny step at a time. It might take hundreds of stages, but eventually, streams emerge that are enriched enough in one element to call them by name: a neodymium, praseodymium stream, a samarium europium gadolinium stream, and so on. You push neodymium and praseodymium into one corner, away from cerium and lanthanum. You push dysprosium and terbium into another corner, separate from their lighter cousins. When it's all done, you precipitate the rare earths out of those solutions as solids, often as oxalate powders, then fire them in a furnace to convert them to oxides. Now you have something marketable, let's say a drum of neodymium praseodymium oxide, often called NdPr oxide, for short, which might be 75% neodymium, 25% praseodymium, or some ratio like that depending on the ore. According to the USGS in 2025, that separation step, getting to individual oxides, is still the most tightly concentrated choke point in the global supply chain. Few places can do it at the needed scale, which is why a room full of mixer settlers in China can feel as strategically significant as an oil refinery. From oxide we go to metal. Our journey's gram of neodymium probably gets trucked to a plant that can reduce oxide to metal. If we're continuing the Mountain Pass story, that's Fort Worth, Texas, where a brand new facility is tasked with this step. They take oxide and either mix it with another metal, like iron alloy with a dash of fluoride, and heat it so that another metal, for example, magnesium or calcium, will grab the oxygen, or they dissolve the oxide in a molten salt and run electricity through it to deposit neodymium metal on an electrode. Let's say they use a metallothermic reduction with a bit of electrolysis cleanup for purity. Now they have neodymium, praseodymium metal, a mish metal, mixed metal, that's ready to be turned into magnet alloy. They add the right amounts of pure iron and a sprinkle of boron, plus maybe a dash of other elements, like a little aluminum or copper, depending on the recipe, and melt it all together. Then the alloy gets strip cast into ribbons, hydrogen cracked into powder, milled down and aligned, pressed and sintered, just as we described earlier. The end result, a stack of shiny magnet blocks, each maybe a few inches across, plated and ready to be cut into the exact shapes needed. Those magnet blocks get sliced into arc segments that will fit into a motor's rotor. At the motor factory, technicians, or robots, place each magnet precisely in the rotor, bond them in place, often with high-strength adhesives that can handle the centrifugal force, and then a retaining sleeve might be pressed or wound around them. The rotor is balanced like a tire to make sure it doesn't wobble at high speed. Now the rotor, loaded with our neodymium magnets, is assembled into the motor with the stator, the stationary coil assembly. When that motor is finally put into a car or wind turbine or robot, it is expected to live a life of vibrations, temperature swings from freezing cold to smoking hot, and exposure to whatever environment it's sealed in, which could be humid, could have oil mist, etc. Any single failure back up the chain, say the acid plant at the mine runs out of acid and the supply of oxide dries up for a month, or one batch in the separation plant comes out off spec, or a magnet coating line had a contamination that leaves tiny pinhole defects, any of those will show up eventually as a problem at the end of the chain. Maybe it's a delay in production, maybe it's a recall or warranty issue years later. That's why when you read headlines about new rare earth mine opens, you should mentally subtitle it, Chapter 1 of a very long book. It's the later chapters, scaling up the separation, perfecting the metal making, achieving high-yield magnet fabrication, and ensuring final products meet spec consistently, where many grand plans stumble. Different companies have read that book and drawn different strategies from it. Some, as I mentioned, are vertically integrating just enough to secure supply. They'll sign contracts up and down the chain or even co-invest in a mine to make sure they have the materials. Others diversify technically. They might say, we'll design half our fleet with magnet motors and half without, so we have a fallback if magnets get expensive. Wind turbine manufacturers might sign long-term deals with both a direct drive supplier and a geared turbine supplier, so they have a portfolio of options. Appliance makers might quietly redesign their widgets to use 20% less magnet material or to tolerate a slightly weaker magnet by using a slightly larger one if they sense trouble on the horizon. And as I noted, a lot of the risk mitigation happens in the supplier management realm, auditing suppliers, qualifying multiple sources, keeping a bit of extra inventory, things like that. I want to talk about a fiasco that you will never read about in the news because it's handled quietly behind closed doors, but it illustrates why building resilience is such a painstaking process. Imagine a magnet supplier discovers that one of its coating baths, say for nickel plating, had a little too much water content on a certain day. Not enough to cause immediate flaking, but enough that after a couple thousand hours in a salt fog test, magnets from that batch start to show tiny blisters under the plating. Nothing in the field has failed, no end user even knows about this. But the supplier's engineers catch it in their routine long-term testing. What do? They isolate the affected batch, traceability at work. They tell the customer something like, "We discovered a minor issue in lot number X of magnets, and we will proactively replace those magnets or ensure they won't be used in critical components," and then they root cause the problem. Maybe they find out the pretreatment solution's pH was slightly out of spec on a humid Tuesday when that batch was run. They tighten the spec, adjust the process, maybe retrain a tech or tweak the drip rate on a rinse. It's not heroic, but it is expensive, reworking or scrapping a batch of product, extra lab tests, man-hours for analysis. However, by doing that, they likely saved a customer from a potential field issue down the road, and they cemented a bit more trust. This is how some supplier relationships turn into long-term partnerships that almost look like marriages. It's cheaper and better for both sides to handle a problem quietly and early than to ship it and have a very public, nasty surprise later. The alternative scenario is the supplier ships those magnets, the car company or wind turbine company finds out a year later when some units in the field corrode, and then it's a huge mess with angry emails and maybe legal action. No one wants that. So you won't see a headline about this kind of near miss, but it's happening behind the scenes, and it's part of what distinguishes a mature, reliable supply chain from a fragile one. On the research frontier, the mood today is pragmatic. There are papers and pilot projects exploring ways to do separation and magnet making differently, trying to find that next edge. For separation, people are testing things like membrane extraction, using special membranes to get sharper separations with less solvent, or chromatographic methods, sort of like how we purify chemicals in a lab but scaled to industrial levels, or even electrolytic separation, using electrical fields to tease the rare earths apart with clever electron moves. Each of these has shown promise in the lab, but the challenge is proving it can work at hundreds or thousands of tons per year without introducing new headaches. It's one thing to separate a few grams of two rare earths with a fancy membrane, it's another to build a plant that does it continuously, with real-world feeds and real-world impurities, and to train a workforce to operate it reliably without inventing a dozen new failure modes. On the magnet side, researchers are playing with additive manufacturing for magnets. Imagine 3D printing a magnet shape directly or making bonded magnets layer by layer. This could allow new geometries or easier incorporation of recycling, with new binder chemicals that might make magnets easier to recycle in the future, binders that dissolve in mild solvents, say, and with tweaks to alloy recipes, like slightly different grain boundary additives, that can nudge a magnet's coercivity up a bit more without relying on as much dysprosium. These are mostly incremental wins. But the thing about incremental wins is they compound. Enough little improvements, 1% better yield here, 2% tighter property distribution there, and suddenly your overall production process is significantly more robust and cost-effective than it was a decade ago. Designers of motors and generators are also learning to be kinder to magnets without diminishing their performance. As we noted, rotor designs that shield magnets from the harshest opposing magnetic fields are now common in high-speed electric motors, so-called buried magnets or clever flux path designs. Control strategies can modulate the torque contributions so that the magnet coasts a bit under conditions that would stress it and then takes on more load when it's in its comfort zone. Thermal systems, cooling loops, heat sinks, in EVs are often designed in part around keeping the magnets and the motor in a happy temperature range. It's not that magnets are fragile snowflakes, but because a magnet that stays 20 degrees Celsius cooler can let you use less dysprosium or terbium in it, which is a huge supply and cost win. None of these approaches scream innovation in a press release, but added up, they make a difference in how much critical material you need and how reliably things perform. If you're looking for a one-sentence playbook that cuts through all the melodrama in this field, it would be, focus on the verbs, not the nouns. Measure how long it takes to train an operator who can keep a separation plant steady on the graveyard shift. Measure how many days or weeks a magnet coating line can run without any drift in quality. Measure how quickly you can switch your rotor assembly line from one adhesive to another if you have to, without tanking your yields. Measure how readily your design can accept a magnet with, say, 2% less heavy rare earth content. Because you improved the rotor geometry. Those aren't sexy things to measure, but they translate into real resilience. You don't have to outmuscle a country that has a near monopoly on rare earth processing by sheer force or rhetoric. You can outprocess them by being boring and diligent. Boring the competition might not sound like a rallying cry, but it works. The end consumer, by the way, never sees any of this if it's done right, and that's the goal. A power steering system in a car that quietly works perfectly for 12 years straight is the sound of a magnet that was never asked to operate outside its comfort zone. A wind turbine that spins contentedly until it's scheduled for retirement is the result of coatings, adhesives, and design margins doing their job to protect the magnets so well that nobody ever had to think about them. You'll read about mines and you'll read about prices in the news, because those make headlines. But every time your electric device turns on and just works smoothly, you're experiencing the real story, the story of attention paid to those petty tyrants like pinhole defects and batch temperatures and maintenance schedules. In the world of critical materials, it's the glamorous nouns that get you into the conversation: neodymium, wind turbines, electric vehicles. But it's the petty verbs that decide whether you get invited back the next day. Let's end with an image, a single snapshot that captures what all of this means. Imagine a motor rotor on a workbench. It's got a dozen or so arc-shaped neodymium magnets glued inside it, each with its shiny protective coating. There's a tight carbon fiber sleeve around the outside holding them in. The rotor has some markings from balancing, and a technician in the factory is giving it a final wipe with a cloth, removing a fingerprint or a smudge from one of the magnets. Why wipe a fingerprint? Because even something that trivial is a potential site for corrosion or a crack initiation if left over time. That rotor, when assembled into a motor, is not going to introduce itself to the end user with fanfare. It's just going to do its job, accelerating a 2-ton car from a stoplight with a feeling of inevitability, or generating electricity on top of a wind tower in January without a fuss. That sensation you get, as a driver, as a consumer, of everything working smoothly and effortlessly is what neodymium buys you when everything from geology to engineering to policy to plain old weather has cooperated under disciplined management. It's not a miracle metal, it's the result of 1,000 little actions done correctly in sequence, even when conditions aren't perfect. Neodymium magnets, and the supply chain behind them, excel when the August heat is brutal, when regulations tighten, when the budget is lean, because people made sure all those verbs in the process kept working in harmony. In the end, it's not magic, it's mastery.